Hey guys, my name is David Zhang, and I'm kind of a computer science geek, so I love math. And today we'll be doing what we call modular arithmetic. And this will be for the Summer of Math exposition hosted by 3 Blue 1 Brown. And they're kind of they're a very famous math YouTube channel, and I think what they do is awesome. And in this kind of exposition, they want to make more free math content available online onto YouTube. So yeah, and I'm gonna hop onto that train. So yeah. So modular arithmetic goes and stems kind of under this branch of number theory. And number theory is just the study or the understanding of integers, whole numbers, which go from negative infinity to infinity. Switch it up to red. And so, yes, we'll start with a number line, right? You can go 1, 2, 3, 4, 5, 6, 7, 8, 9. I guess that'll be good enough. And you'll notice that these integers can act in a sort of cyclic manner, or what we call, or a pattern, basically. And for example, let's look at odds and evens, right? This is even. This is odd. Right? You know, there's a pattern. Every 2, you'll notice that there's going to be an even guy. And every 2, there's going to be an odd guy, or odd number, right? Even odd, even odd, even odd, even odd, even odd, even odd. There's more other patterns too, right? We'll take a look at like maybe 3s, right? 0, 3, 6, 9. And maybe these guys too fall into a pattern. And these guys fall into a pattern, right? These are divisible by 3. And these guys are divisible by 3, but they have a remainder of 1. And modular arithmetic is basically, modular, my bad, is kind of the understanding of remainders. So if you remember in grade school, or when you're in like elementary school and kindergarten, you know that when you, maybe, whatever, I don't even know if you learned division in kindergarten, but when you divide something that can't be like easily divisible, right? Because 7 does not go into 29 perfectly. And what you'll do is you'll take the highest possible, I guess, multiple of this number that you can that's under this guy. So in this case, it would be 28, right? And you'll have a remainder of 1. So yeah, that's kind of a brief on remainders. And I guess in this case, we'll say that in order to write it, just say 29 mod. So this is the mod symbol or modulus. Mod 27 equals to 1. And yeah, so there's always a pattern, right? With modulo, you'll always find a pattern. And a good way to remember that, or a good way to remember modulo, is through a clock. You'll notice that a clock always goes in the same pattern every single day. Yeah, so maybe you'll start at 1 and it'll tick, 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 tick to 11, 12, and then it goes back to 1. Tick, 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 1. Tick, 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 tick. And keeps on going, keeps on going, keeps on going infinitely and infinitely. So here's a problem, right? Let's say it starts at 1 p.m., right? You're at 1 p.m., maybe you're like drinking a lemonade. I don't know. That's not a lemonade, it's red. Oh no. I am panicking. Okay. Lemonade. And for some reason, I guess, like, you want to try fermenting your lemonade. And that takes 1,000 hours to ferment. What time will it be after that? Now, don't worry about AM or PM, but what time will it be on this clock after 1,000 hours? Okay. And if you're distracted by the lemonade, don't eliminate. Okay. Okay, take out eliminate. Bye-bye. We don't need it anymore. And what happens after 1,000 hours? What time will it be? I'll give you a couple seconds. So, okay, we're back. And you'll notice that, like I said earlier, it follows the same pattern over and over and over again. And that it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then 1, 2, 3, 4, blah, blah, blah. So it repeats every single 12 hours. And just like odds and evens, where it repeats every 2, right? I erased my awesome number line. I'll just delete this guy. We see a pattern. So what we can do is we can divide 1,000 by 12. And you want to look for the remainder. So actually, it would be more like this. And you'll find that equals to 4, because the highest number under 1,000 that is divisible by 12 is 996. And you subtract that, you'll get 4. So that means it'll be 4 hours after this starting point. So after 1,000 hours, it will be at 5. So that's the answer. 5 o'clock. Which is, yeah, it's a kind of cute example. And you'll notice whether it be 4 hours, 16 hours, 20 hours, or even something crazy like 4,252 hours, it will always be 5 o'clock after, that. Because after a pattern of 12, it will subtract 4. Subtract this by, actually not 20, my bad. No. It's actually 28, yeah. Highest power of that, 24, 4, 4, 4. And after modulo, you always get 4. So, and what we can do is we can group these numbers into what we call residue classes, or I don't really say residue classes, but we can say two integers are congruent, let's say A and B, if they both mod whatever, I guess we'll say 12, which usually will be n, would equal to each other. And I usually say congruent. Some people say residue classes. Residue like this. Residue or congruent or equivalent, kind of all the same. And they're the same because when they're divided by 12, they share the same remainder. And formally, we can write this down as like this. I'll switch it up to weight. And in our case earlier, we can replace A with 1,000, replace B with 4, and mod 12. This is kind of what you'll see in like math textbooks and stuff like that, or I don't know, maybe your professor will do this. And similarly, we can do the same with this. So 16 will be the same as 1 mod 3, 79. These are just examples from my script. And the idea of these like kind of classes are a little strange, but you'll realize that like it's not that like A equals to B. It's just that you can jump from like 4 can jump to 16 freely at 12. And it will always end at like 5 p.m. Same idea. Like you'll always end at the same kind of point. And modulo is kind of like a loop. You go in a circle just like a clock. And regardless of how many loops you make, it's going to end at the same area. Yeah. So I guess we'll go into the arithmetic part of it. Right? Just like normal basic arithmetic, you know, A plus B equals C, you'll notice that if A is congruent to B, mod n, of course, and C is congruent to D, mod n, A times A plus C equals to B plus D, of course, mod n. Same idea with multiplication. I don't know why I put the dot there, but whatever. That's not mn. Mod n. And yeah, so I guess we'll do some examples. This also works for subtraction and division, but that's a little hard to explain. And if you want to dive a little bit more deeper into it, I recommend looking at Second Thread. Second Thread. He's kind of this like big competitive programmer, which is part of computer science, and he explains how these operations work much better. But I'm just a high schooler, so it doesn't matter. But this guy's pretty cool, and I highly recommend you look at his stuff. But here's some examples of those basics operations, right? So here's a cool question. 3,333 plus 4,444. What is the remainder? Divided by 5. And what is the remainder? Or actually, it could be just modulo. And what is the remainder of their product? And you'll find that if you add these two together, right? So, well, let's just take the mod of each, right? A good way to kind of divide up the problem is another property is we can mod each of these guys. So this guy, mod 5. Blocking. There we go. There we go. Is 3, because 5 usually ends in 0 or 5, and in this case it's less than 5, so we'll take 0 and you'll see that it ends at 3. Right? And 4,444 mod 5 is 4. And if we add those two guys together, 3 plus 4 goes to 7, and mod 5 is 2. Right? And yeah, because if you go in a circle, right, 1, 2, 3, 4, 5, you notice that 1, 2, 3, 4, 5, 6, 7, and it ends on 7 or 2. So similarly, if we take the product, right, we know that 3,333 mod 5 is 3, like we said earlier, 444. Mod 5 is 4. And if we multiply them together, it's to 12, and 12 mod 5 is equal to 2. Right? And in general, we can take any integer and replace it with an integer within the same residue class. So this is the same residue class as this. This is in the same residue class as that. And we can do it multiple times within a problem. Now, yeah, I don't know how it somehow ended at 2 for both, but yeah. So we'll end it off. I'm reaching my 15-minute mark, which I kind of didn't want to pass. Actually, maybe we'll go longer. I'm kind of having fun with this. What is the remainder of 2,115 to the power of 2,115? Right, what is the remainder divided by 2014? So we won't even get a perfect 2015. And you'll note, actually, I'll give you a nice little break. Think about it as I make my font a little bigger. Okay, so how are we going to do this? Well, you'll notice that 2015 to the power of 2015 is just the product of just 2015, 2015. Wow, that's a handful to say. And since 2015 mod 2014 is equal to 1, let's just replace all these with 1, right? Dot, 1. And you'll find that if you just multiply whatever, well, you'll know that 1 to the power of any n is always going to be 1. Okay? And you'll find that the sum of all the, or the product of all these is just going to be 1. So the final, I guess, number, the remainder, is just going to be 1. And you'll see that, like, this just gives you a glimpse into how cool modular arithmetic is. And, you know, instead of busting out a calculator and doing this 2015 times or taking forever to do it, it just seems like too, I guess, a good way is like impossible. It's just too crazy of a number with like a billion digits. And literally we just did this in like 2 seconds and we found out the last digit or the remainder, just dividing it. Yeah. So yeah. This is kind of, maybe we'll stop here. But yeah, I'll just stop. But maybe I'll probably go into a part 2. But this is kind of how powerful modular arithmetic is, and I just wanted to give like a little basic introduction of like the little bits and pieces. So yeah. Goodbye.